Hello everyone, today I'm going to present a short lesson on statistics. I'm going to talk about z-test, t-test, population mean and standard deviation, sample mean and standard deviation, and the relation between the two. Let's start with an example. Let's assume we want to find the average height of all males in the US. So the population that we deal with is 150 million people. So we cannot survey all that people, but we can take a sample of that and then take measurements of our sample data. If our sample is more than 30, according to central limit theorem, we can assume that our distribution is normal. So we are interested to find the population mean, which we show by mu, or population standard deviation, which we show by sigma, but we only have access to our sample mean and sample standard deviation. So we want to find mu and sigma by analyzing Xbar and S. So the symbols are important. Remember that we show the sample mean by Xbar and the true mean by mu. Same thing for S and sigma. But if we take more than one sample, in addition to finding the sample mean, we can find the mean of all sample means and the standard deviation between different sample means. So we can relate the two in our analysis. So the mean of all sample means would be equal to our true mean or population mean. Still, that's not really helpful because we do not have access to the mean of all sample means either, but we are going to use it in our analysis. The other relation is between the standard deviation. The standard deviation of X bar, the variation between the sample means, is equal to our population standard deviation divided by the number of data that we have in each sample. So this equation tells us that if the number of data point increases, let's say the number of data point goes to infinity, what happens to the standard deviation of our means? That would go to 0 because n is in the denominator. So that means that if the number of data increases and our sample becomes so large that is basically the population, then the difference between these samples that we got would be negligible. There won't be any difference between them because all of them are representing the population. Now we are going to define another important parameter for us, the z-value. So if we look at this distribution, we have an average value. It could be mu x bar, but now I'm just presenting the definition of z-value. And if our distribution has a standard deviation of sigma, if we want to find the location of our data x bar, x1, we show it by how far it is from our average value. So if our data is 2 standard deviation away from our mean, the z-value would be 2. So similarly, if x1 was on the other side of mean, z-value would have been negative. So instead of reporting the distance, we use a unitless value to report how far is our data from the mean. So x1 would be mu plus 2 standard deviation, or z standard deviation. So the z-value would be x1 minus mu divided by our standard deviation. The z-value and confidence level go hand in hand. There is always a confidence level associated with our z-value. So for this z-value here, we can think of a confidence interval, the area under the curve, that is confined between z negative 2 and z2, and that would be 97%. It's not 100% because the data could be at each tail of our distribution, but we are confident that 97% of data would fall between z negative 2 and 2. So for every z value there is a confidence level, and for every confidence level there is a corresponding z value. Here we are going to look at the z-test. Again, we have a distribution, but here I'm showing you the distribution of all the means. So Xbar is one sample mean, and mu is the mean of all means. Similarly, I can present Xbar with respect to z and mu. So Xbar would be mu plus minus z times the standard deviation of our means. I here use plus minus because Xbar could be on the other side as well. Our standard deviation of the mean, we already presented the relation between the two, would be our standard deviation of the population divided by the number of data in our sample. This equation, we can rewrite it as function of mu because we are interested to find the mean value, not just our sample mean. We already know the sample mean. And plus minus z, the standard deviation of our means. If I replace the equation for the standard deviation based on the standard deviation of the population, I will get this equation that we commonly use to find confidence level, probability, and so forth. So we are using the z-test to find the population mean based on the assumption that we have the population standard deviation. In practical problems, if we have no information about the population mean, we usually don't have the standard deviation of the population either. But statistically, if we know it, we can use the z-test. What happens if we don't know the standard deviation? We can use the t-test, or sometimes it's referred to as a student t-test. Everything is the same except we are using S, our sample standard deviation. So we have access to our sample, we know X bar, the mean, also we know S. So we can find the population mean based on t-value and our sample standard deviation. T-value is different than z-value because it's not only is function of the probability, but also is function of nu, which is degree of freedom, which is the number of data point minus 1. As the number of data points get higher and higher, the t-value get close to z-value. If you remember that number 30, if the number of data point is higher than 30, the t-value and z-value would be close. I mean, in the statistics, they say that if the number of data point is more than 30, you can use z-value. But in my opinion, if you do not have sigma, always use t-value. T-value is more accurate. Nowadays, we have access to software that give us the t-value. There is no reason to use z-value. So if you're taking my class, when you don't have sigma, always use the t-value. And t-value sometimes is reported as function of alpha, which is 1 minus p. So 1 minus the probability. It deals with the two tails of our distribution. So let's look at an example of how to find a z-value. This is a z-table. In the z-table, the first column are the z-values. The first row is the decimal place for the z-values. So here, if I want to find 0.23, this would be 0.2, and then 0.2, 0.21, 0.22, 0.23. So I deal with this value of the probability. Let's look at an example. Find the confidence level or the probability associated with z equals 2.08. So let's go here. We have 2.08. So this is 2.0, 2.01, 02, go all the way to 2.08. So the value of our confidence level would be 98.12% or 0.98. That's the value for our probability. Now we are going to do the opposite. We want to find z if we have the probability. So the probability is 99%. What is the corresponding z value? So we have to go here and find 99. So here I have 98, it increases. Here I have 0.9901 and 0.9898. So it would be between the two values. What is here is 2.3. We are between the third column and the fourth column. So 2.325 between the two. You can interpolate between the two and find the exact value. But for most cases, just averaging the two would be enough. And here is the t-value. In a structure, it's very similar to z-value, but the difference is that we have degrees of freedom as well. If you remember, we said that the t-value is not only function of the probability, but it is function of the degree of freedom as well. So in this problem, we want to find t-value, not z, this is the t-table, associated with the probability of 99 and degree of freedom 30. So we need the degree of freedom as well. So here we have 30, probability of 99, it goes, here I have 99, so that would be 2.75. So here we can go and look what happens if the degree of freedom increases. So at the beginning, the changes is drastic. You go 63, 9, 5, 4, and as the degree of freedom increases, the changes become negligible. So that magical number of 30, you can see it's not really magical. It's 2.75, 2.70. Still we have an error between the two. And when it increases to more than 1,000, then you can see that the z value and t value would be the same. So in the last row, z value is reported after the degree of freedom of 1,000. So z values and t values are not really the same after 30. Use t value all the time if you don't have sigma. So we can use software such as Matlab and Excel, which are very common software in engineering, to find the t values. The function in Matlab is tinv. The function in Excel is also tinv. So at the first glance, it might look as if we have the same function for both, but it's actually very confusing. The first difference is that Matlab uses probability, p, as one of the input. Excel uses alpha, which is 1 minus p. So that's a major difference that you need to be aware of. But both of them use degree of freedom, nu, which is simply the number of data point minus 1. Matlab is based on a one-tail distribution. So here I'm showing you a one-tail distribution. Excel is based on two-tail distribution. So if you have a t-value here, the corresponding t-value for this will be here. That's the two-tail distribution. Excel deals with alpha, so 1 minus p, these areas, the two tails. Matlab deals with the probability. These two are equivalent in each software. So if we have a 99% probability, and let's assume a degree of freedom of 25, in Matlab you have to plug in 99%, degree of freedom 25, it gives you the corresponding t-value here. In Excel, the t-value, that would be 1 minus the probability, or 0.0225. So these two values are going to be the same. One you plug in Excel, the other one in Matlab. To me, Excel is more intuitive. If I want to find the confidence interval of 0.98, I just simply say 1 minus 0.98 would be 0.02 and plug it in here. And I get my t-value. For Matlab, I have to actually think about it, that 98%, that means that at each tail, I have 1%. And because it's probability, I have to use 99. It's okay if you use either, but you just need to know these two fundamental differences between Matlab and Excel that has caused a lot of confusion and a lot of errors. Matlab has bunch of more functions related to z-value, t-value, and probability. One is that we discussed, you plug in the probability and degree of freedom and you get the corresponding t-value. You can do the reverse. If we have the t-value and degree of freedom, we can find the probability. Also, Matlab has a function called z-score, which is very confusing. It doesn't give you the z-value based on the probability, but it gives you, finds the z-value for a set of data. If you have a set of data 2, 3, 56, 34, 23, if you use the Matlab function z-score a, it finds the average, it finds the standard deviation, and it finds the z-value for each case. So in summary, first we should know whether we have sigma, the population standard deviation. If we do have it, then we can use the z-value and the population standard deviation. If we don't have sigma, then whether our data is more than 30 or not. If it is more than 30, we can use the z-value. But because we don't have the population standard deviation, we use the sample standard deviation. If our data is not more than 30, then we have to use t-value and of course the sample standard deviation. But my recommendation again, if you don't have sigma, if the answer is no, just use the t-value. Here we are going to talk about the statistical difference between two means. So let's look at an example. We want to find the tensile strength of steel at room temperature. If we do testing once, we get one data point. If we test multiple times, we get a distribution. Our distribution will have an average value and a standard deviation. If we raise the temperature to 200 Fahrenheit and do the testing, we will get a different distribution that will have a different average value and a different standard deviation. But because they are different, it doesn't mean they are statistically different. Of course, there is going to be a variation between the two. That's with any data point. Here we are going to evaluate whether that difference is within margin of error or actually the properties are changing with changing the temperature. So we are going to look into whether these two are statistically different. So let's go back to our main equations. Our population average was based on the sample average, the t-value, our sample standard deviation, and the number of data. If we have two means, so we have two of these equations. If I want to find the difference between the two, I subtract them. mu1 minus mu2, xbar1 minus xbar2, that's the typo, plus the t-value. And here I'm dealing with pool standard deviation. So here for the t-value we have nu and alpha. Alpha is 1 minus p, the probability or the confidence interval that we are looking for. But nu is the degree of freedom. Because we have two set of data points, the degree of freedom is simply the addition of the two. And each degree of freedom was the number of data point minus 1. Nu2 was the number of data point minus 1. And here is the pool standard deviation. Whenever you have a standard deviation squared, that means variance. So basically the same thing, it's just always positive because it's you square it. And here you have it based on the variance of each sample. S1 is the standard deviation, S1 squared is the variance. Here the important thing is that because we have plus minus, so we are going to get a range. And in this range, if this range includes 0, there is no statistical difference between the two means. So think about it. When mu1 minus mu2 would be somewhere in this range, that could be 0. If mu1 minus mu2 would be 0, that means that mu1 is equal to mu2. So there is no statistical difference. But if the range does not include 0, that means that regardless of what value we choose, it's going to be a non-zero value. So mu1 minus mu2 would not be 0. So there is a statistical difference. Let's look at an example. Mu1 minus mu2, if we get this range, a range from negative 2.3 to 1.5. This range is going from a negative value to a positive value. That means that the range includes 0. So there is no statistical difference, because mu1 minus mu2 could be negative 2.3, could be negative 1, and could be 0. So it could be a case that these two are the same, and that means that there is no statistical difference. The differences are above and less than 0. Here, another example, this range is all in negative 2.3 to negative 1. That means that this range does not include 0, so there is a statistical difference. Mu1 is always less than mu2. So when we are moving from condition 1 to condition 2, actually we are getting lower value. If we think about our example, so that means that the property in the second condition are lower than the property in the first condition, because the range is in negative value. And that's how we can tell whether there is a statistical difference between two set of data, because the data itself is always going to be different. But how different is it? Is it large enough that we could say the two data are from different populations, or are negligible?